In this lecture, we are going to recapitulate some feedback and feed-forward control method in switch mode power converter. So, here we are first want to recapitulate our analog feedback and feed-forward control, and we want to just summarize what are the primary objective using feedback and feed-forward control. Then we will also talk analog voltage mode control, which is an example of single loop feedback control. Then we want to recap analog current mode control, which is a good example of two loop control, and then we want to recap input voltage and load current feed forward actions. So, in this lecture we want to have an overview of feedback and feed forward control method. Here I am showing a buck converter example, but there it can be any other converter, and here I am showing that there is a current sense amplifier, and this current sense as well as the voltage sensor. This block consisting of the sensing circuit as well as the feedback resistive divider and some signal processing like impedance matching and so on. Then after output, the output of this sensing block will come to the feedback and feed forward control block, and we have discussed in detail in our earlier NPTEL course all this detail as well along with MATLAB implementation, and ultimately this particular signals has to be converted into gate signal. So, you need a modulation technique. So, here I am showing a simple pulse width modulation by using a latch as a comparator. So, you can synchronize with a fixed frequency clock, that is why it is a pulse width modulation, and by means of a comparator and a latch circuit you can generate duty ratio of this converter. And role of feedback control. So, here the feedback control as well as feed forward control, we have certain objectives and their functions. So, first of all we need to regulate the output voltage, we need to achieve very fast load transient, that means we need to meet certain load transient requirement. We need to protect the current limit. If you take a boost converter for example, without current limit your switch can switch can burn, the whole power converter can collapse if you do not take proper current limit, okay, or it can damage your switches or even it can saturate the inductor. Then supply disturbance, input supply disturbance, which is also very important, and also we need to reduce EMI. So, these are the aspects which are part of the objectives for designing the feedback control. Then we need to achieve almost flat efficiency curve over a wide load current range, and this is very important, and this will be very difficult and challenging if you are going for light load, and we may have to shift the control technique or modulation technique from one modulation to the other modulation. And these are the consideration, that means we need to also take care the fast scale and large signal stability, that means there should not be any subharmonic oscillation or the system should not collapse, that means large scale the system must be stable. And the constant is that the variation in on and off time of this gate signal should have a limit, because we will have a limit in terms of switching frequency, because the driver may not support, the switch rise time fall time may be a constant, and there can be boost trap arrangement for the high side circuit that also requires some time for charging and discharging. So, all this should have some constant on the on off time. Next, we have discussed in our earlier course, that means feedback and feed forward control, like voltage mode control with and without input voltage feed forward, current mode control with and without droop control, then state feedback control, linear and nonlinear control, fixed and variable frequency control, multi-mode control, and all these controls are actually interdependent. With the modulation and control, they will go, they are not totally independent. Like if you take a feedback voltage control, you can use either pulse width modulation and you can also use constant on time modulation. Similarly, in current mode control, you can have various modulation technique which will translate your feedback signal into the duty ratio on off time, okay. And all these details have been discussed in the previous NPTEL lecture, like a control and tuning method in switch mode power converter course. So, I am not going to discuss detail of this, but I just want to take some gist of this analog control before we start the digital control. So, if you take a single loop feedback loop control, the general architecture of any feedback control, it consists of you need to control the plan, some output to meet some desired response, and we take generally the feedback control, there can be some measurement noise, sensor, then this will be compared with the reference signal and there is a controller, right, and finally the output of the controller will go to the actuator and that will generate the signal. And the disturbance can be load disturbance, supply disturbance. So, if you link with the power converter, then this controller is nothing but the compensator, like you can use a type 2, type 3 compensator, or even if you use a PID controller, then this actuator is nothing but a PWM and there is a gate drive circuit, and that PWM will convert the compensator output into some gate signal. When you say PWM, that means we are generally assuming that switching frequency is constant, but it is not necessary. We can have also constant on time, off time, or hysteresis control, but ultimately you need a gate driver to generate the controllable gate signal for the MOSFET. And then if we model small signal model that we have discussed, so there will be a control to output transfer function, and then you need to control the output voltage, and there can be load current variation. So, you need to assess the output impedance, then there can be supply variation. So, you need to know what is the open loop audio susceptibility and what should be the design objective as well as the control objective to make the output voltage more or less insensitive to supply disturbance, or you need to meet certain load transient requirement, that means in terms of overshoot, undershoot requirement and so on. And this can be, you will get detail of this in lecture number 15 in the previous NPTEL course, and you can get the link from here. Now, basic two loop control, if you consider, we generally consider an inner loop, which is generally the current loop for DC-DC converter, which is considered to be pretty fast. Then you can have an outer voltage loop, which is a slower loop, and this kind of control are known as two loop control. It can be master slave control or cascade control. And the outer loop are generally kept the output voltage loop, and the inner loop can be inductor current loop in case of current mode control. It can be capacitor current, but capacitor current is generally, if you want to sense directly the capacitor current, that may not be recommended, because if you introduce any additional resistance, that will increase the ESR. So, that can increase the ripple, and it can also create a DC drop when there is a large low step transient, that can also impose a large voltage sudden jump. So, that is why by sensing capacitor current by means of resistive sensor is not recommended. And you can also take the derivative of the output voltage. In fact, we have discussed in the previous lecture, if we incorporate the derivative of the output voltage, you can have time optimal recovery in voltage mode control by suitably selecting the controller gain. So, we are not going to discuss detail, this have been discussed already, and it can be also ripple output voltage can also be the outer loop, because this is for ripple based control, okay, and you can get detail about this in lecture number 15 in the previous course. Now, in single loop feedback control, if you take a DC-DC converter, which is a voltage mode control we call, here you can have a PWM block and there is a latch circuit, and we have discussed, and this is a trailing edge modulation, and we have discussed this latch action can introduce some delay, and we have also discussed how to design this compensator, and we have validated this design using MATLAB switch simulation. And we have also discussed that what are the limitation of single loop control, because single loop control there is no control over current in voltage mode. So, you will have a difficulty in terms of limiting the current, particularly for fault protection, startup transient. Then the compensator design can be sensitive to operating condition, because if you want to design a type 3 compensator, then this you need to also take into account the load current variation. If you know the inductor and capacitor, and if there is a variation in the LC also, so your compensator design is very critical when you are talking about the worst case based design scenario. Then you need to consider the fault protection and the startup logic. These are also very important, and this can be a slightly difficult in voltage mode, because if you take a startup in voltage mode startup logic, you need to intentionally keep the process slow, because there is no control over the current. So, you need to make sure the current should not go out of the the safe limit, and this kind of single loop control may be difficult to optimize transient performance, but this statement is applicable for small signal. If you go for large signal, you can even achieve the fastest response using single loop control. So, these are all design perspective, and we are mostly talking about the small signal based design. If you are talking about a current mode control, it is a good example of two loop control, where you have an inner current loop, which is an inductor current feedback loop, and this current loop gain is decided based on how are you sensing the current. Suppose if you use a resistive sensor, then there is a sense resistance, voltage of the sense voltage will be that resistance into the current. Then after that you need to put a current sense amplifier, so the gain of the amplifier. So this Kc is a combination of the sense resistance multiplied by the current sense amplifier gain. So this whole will appear like a gain, which will translate the actual inductor current to a sense voltage, and this sense voltage will constitute an inner current loop, and this takes the current dynamics, fast current dynamics. So you need to also consider the suitable current sensing method, so that you don't lose the vital information of the current. So you need to be careful about the selection of current sensing technique, then what is the right current sense amplifier, the bandwidth, and all will come into picture. Then outer loop is typically a voltage loop, and this feedback voltage gain is mainly due to the resistive divider, because we need to step down the voltage, and this voltage will be taken as the input to the compensator, which is a op amp, and we need to make sure that such voltage should not exceed, or the error, it should not saturate the op amp, because op amp in most of the commercial product, the op amp will have a single supply rail, and it is 0 to 3.3 or even less depending upon the process technology. So you have to be careful about the selection of this feedback gain. Then you have a reference voltage and error voltage, and that is multiplied by the voltage controller. And we have discussed in detail lecture number 15 as well as the lecture number 38 and 39 how to design a voltage compensator for a current mode control. So you can get detail about this. So we are not discussing, but we need to first recapitulate the analog current mode control, which is a two loop control. What are the advantage? Because of the two loop, actually you have an inner current loop and the outer voltage loop, and if you take the transfer function between this point to this point, by virtue of closing the inner loop, you will get, because originally the DC-DC converter, if you take voltage mode control or direct duty ratio control, that means you are directly controlling the duty ratio, then the dynamics will be driven by this LC. So you will get, naturally you will get a second order behavior due to the LC pole, the filter. Now when you close the inner current loop, then you are essentially making the inductor behave like a control current source, and virtually the system will behave like a fast order system. So by closing this feedback inner loop, you can make the system the control to output transfer function between this point and this point like an approximate fast order model, and that will simplify the design. This is one of the major advantage of using current mode control. So you can get a reduced order dynamics using time scale separation, because you are actually making the inductor like a control current source. So basically we are assuming the inductor dynamics is pretty fast compared to capacitor. So the pole due to the inductor will go far left hand side. So you can get a time scale separation. Then because you can approximate by a fast order model, so you can simplify the design, controller design, and you can get a very improved robustness, because there is no L dependency in the design. So you can make the design much robust. Even there is a variation in the inductor, because as long as you control the current properly, there is no problem. And you can achieve very high bandwidth without compromising phase margin. But there might be a problem in current mode control, because you are only making a fast order system. The response can be sluggish, and you may end up with a very overdamped response. And if you try to push the bandwidth to achieve fast response, then we have discussed in our earlier lecture, the model validation is a concern. So you cannot go even beyond 1/5 of the switching frequency, then your model will start diverging and the design is invalid. So within that limit, if you want to design this overdamped system, then you may have some problem, and we have discussed how to overcome. Either you can add directly load current feed forward, or you can incorporate some kind of voltage derivative action by replacing inductor current. If you consider the voltage derivative action, this inherently retain the inductor dynamics, plus it also add the indirect load information. So you can achieve very fast transient using this technique. But one of the major difficulty is the current sensing. If you are going for high frequency application, then there can be some problem in the current sensing. But if you go to integrated circuit, that means IC, then you can actually play with various current sensing technique. You can sense just the high side current by means of RDS on, that is switch. You can use some kind of a current mirror and you can sense the current. But depending upon what kind of current mode control are you going, because we know about peak current mode control, we know about valley current mode control, we know about average current mode control. So based on our type of control, then we need to particularly sense the current. For peak current mode control in a buck converter, we need to sense high side current. For valley current mode control, we need to sense low side current, and it is much easier to sense low side current, and that's why we have also discussed the commercial product, latest product is going towards constant on time current mode control. So we have discussed this in our earlier course. But in current mode control, fixed frequency, let's say peak current mode control or valley current mode control, we saw there are stability issue in the inner current loop, and particularly when you deviate from the 50% duty ratio. For peak current mode control, if you go even below 50% and above, let's say around 0.4 or so, go above, you may end up with inner loop current loop instability. For close, when both the loops are closed and you are operating at a higher gain, so you may end up with subharmonic oscillation. Similarly, for valley current mode control at low duty ratio, you will get substantial subharmonic oscillation problem. And we also discussed, in order to overcome, we need to add ramp compensation. But excessive ramp can also make the system slowly, it will behave like a voltage mode control. So these aspects are discussed in the previous lecture, and we have also discussed the input voltage feed forward, because voltage mode control suffer from poor line regulation as well as audio susceptibility. So you can make the output voltage more or less insensitive to input variation in a buck converter if you can change the ramp. That means this ramp slope can be adaptively varied based on the input voltage, and this can be implemented by means of a voltage control current source, and this current source can charge a capacitor to generate the sawtooth waveform. So this can be, and many commercial IC use that, and we have discussed this aspect in lecture number 14, so you can refer for further detail. Similarly, we have also discussed load current feed forward in current mode control, which can make the output impedance extremely well, behave like a something resistive droop, and you can actually have a ultra fast transient, and suitable design can lead to time optimal recovery. And this also we have discussed in lecture number 17, that the load current feed forward methodology. We have also discussed, along with load current feed forward, if we incorporate the droop mechanism, then you can achieve very fast transient, and you can make the output impedance virtually look like a resistance, so that it will be almost frequency independent output impedance, and you can respond to the load transient very fast, almost instantaneously. So this aspect also we have discussed in lecture number 17. So we have discussed. Now the question is, when you go to digital control, how to digitize this single loop and multi loop, that we have recapitulated in our analog control, right, in this lecture. These are the questions that we will be addressing throughout the course. Then what are the design flexibility? What will design flexibility be using these various modulation techniques? Then how many ADC and DAC will be needed to realize digital control? Then how to incorporate feed forward action in digital control? So for this, these are one of the objectives of this course, and this will lead to various architecture development using digital control. Even for peak current mode control, you can have 3-4 type of architecture in digital for implementation point of view. So you need to wait for this architecture exploration, which will be coming soon. So in summary, we have discussed, we have summarized the primary objective using feedback and feed forward control. Then we have recapitulated analog voltage mode control, example of single loop control. We have discussed current mode control, which is a 2-loop control example. Then we have recapitulated input voltage and load current feed forward action, and in the subsequent lecture we will slowly digitize this analog loop, and we want to see the number of ADC and DAC requirement. So with this, I would say that this is the first step to go for digital control, and the method of digitization that will be discussed in the subsequent lecture. So with this, I will finish it here. Thank you very much.